events, cause and effect. We analyse what went right and what went wrong, as we discover that many outcomes can be predicted, planned for, and even prevented. I'm John Chidgey, and this is Causality. This episode is sponsored by Makers for Good and their impressive HELIO solar-powered light, flashlight, and powerbank that's perfect for camping, hiking, emergencies, as a nightlight, or for wherever your adventures may take you. We'll talk more about them during the show. Causality is part of the Engineered Network. To support our shows, including this one, head over to our Patreon page. And for other great shows, visit engineered.network today. Milford Haven. This is the second in a series of episodes with a focus on control systems' contributions to disasters. The first, regarding 3 Mile Island, episode 17. The incident at Milford Haven is a bit different from the other incidents insofar as it seemed quite complicated, but in the end, there were still things that could have been done to prevent it. It was a second major incident in the series of incidents globally that led to improvements directly into how user interfaces are designed. But we're getting ahead of ourselves. The Pembroke Refinery was built on the banks of the Milford Haven waterway in Pembrokeshire, Hundleton, in United Kingdom, more specifically southwest Wales, and it opened in 1964. When it opened, it was owned and operated by the Region Oil Company by name only, as Region Oil had been acquired by Texaco some 8 years before it opened that site. It remained with Texaco until it was acquired by Chevron in the year 2000. The plant produces petrol, otherwise known as gasoline, diesel, kerosene, and liquid petroleum gas, or LPG, from crude oil. The plant had a maximum production of 190,000 barrels per day at the time of the incident, with oil tankers delivering crude oil for processing from the harbour. The refinery itself comprises of 2 different sections. Each is operated by a different company. The Pembroke Refinery operated 10 process units, with the cracking components comprising 8 units in total. They were operated by the Pembroke Cracking Company, or PCC for short. The incident itself occurred in the Pembroke Cracking Company section of the plant. The PCC was a joint partnership between Texaco Limited and Gulf Oil Great Britain Limited. The arrangement resulted in a common facility with many process connections between the 2 companies' equipment. However, the site had a mixture of employees from each company present throughout. The refinery process area employed approximately 150 full-time staff, with the cracking area employing about 120 full-time staff, with much of the works required executed via a contractor model comprising up to 400 people that fluctuated based on shutdowns, overhauls, and other major works in progress. Oil refineries typically follow a continuous process flow whereby crude oil is introduced into the feed end of the plant, and each subsequent stage extracts subsequently lighter components. In terms of the gases that can be extracted from crude oil, the progression of gases from lightest to heaviest is methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane, where methane has a single carbon atom surrounded by 4 hydrogen atoms, and decane has 10 carbon atoms with 22 hydrogen atoms surrounding it. Since petroleum liquids have no use of gases, those gases are extracted and removed from the liquid in subsequent stages of the process. There were times before the 1970s and 80s where these gases were simply burnt off or flared, as they were considered to be a waste byproduct. However, in time, with the cleaner burning nature and subsequent market demand for these gases, refineries began to capture them instead, compressing and or sometimes liquefying them and selling them as their own product. And in this case, that was the LPG, and that was one of the products extracted from the crude oil at Milford Haven. However, so far as the process flow goes, the refinery has many stages. Each is designed to extract a specific component from the oil, and the impact of one stage backs up the stages that feed into it. It also then impacts the stages that it subsequently feeds that follow it by starving subsequent stages of their feed material or oversupplying those stages. Understanding this interconnected nature of process flow in a refinery is critical to understanding exactly how these knock-on effects of process disturbances can lead to an incident if they're not managed correctly. The incident itself. The following time references are based on the Distributed Control System, or DCS, alarm and event log. It's worthy of note to mention that the 4 independent clocks at the plant, the DCS, radio logs, TDAX, data logging system, and the critical process controller, were all different times, in some cases quite significantly, making the exact determination of the correct time and sequence of events more difficult during the investigation. The DCS specifically in use was a Honeywell TDC 3000 system. Early on Sunday, the 24th of July 1994, a lightning storm had passed through the area, with voltage spikes and power dips tripping many items of equipment in the processing plant between 7:49 a.m. and 8:30 a.m. that morning. One lightning strike started a fire on the crude distillation unit, which subsequently caused process upsets in the downstream vacuum distillation unit, alkylation unit, fluidized catalytic cracking unit, or FCCU, and butamer units of Train 2. At approximately 8 a.m., the alkylation and butamer units were shut down and the feed of vacuum gas oil into the FCCU was reduced from 600 to 400 cubic meters per hour as a direct result. At 8:33 a.m., the low liquid level in the high-pressure separator alarm sounded. Any alarms noted following from this moment indicate both visually and audibly on the control system unless otherwise mentioned. In order to recover the level in the subsequent de-ethanizer, its feed valve position was reduced to 36% manually by the plant operator. Despite the fact that the valve should have been significantly open even at 36% and allowing some flow to pass through it, the DCS process flow indicated that the movement of this valve had actually caused all flow into the de-ethanizer to be completely cut off. The feed valve, in this case FV385, was known to be temperamental and had a partly documented, though not fully documented, as being sticky and non-responsive with inaccurate position feedback. The outlet flow from the de-ethanizer to the debutanizer was about 450 cubic meters per hour, and without any feed in, this completely emptied in only 5 minutes. The DCS cascade controller fed this level into the debutanizer, output flow control valve, which then began to close in an attempt to retain some level in its own tank. As tanks emptied and levels dropped in multiple tanks, multiple low alarms were indicated in the control system. Because the flow through the debutanizer had been significantly slowed down and there was no longer any feed into the tank, and hence the material in the tank began to slowly vaporize. This vaporization increased the pressure in the tank as more hydrocarbon vapor was released into the vessel. This caused the liquid level to drop accordingly as the vapor quantity increased, which led to the liquid flow to the naphtha splitter to also stop, causing the splitter level to fall to 0. And it would stay at 0 for nearly 4 more hours until the incident occurred. At 8:51, the reflux pumps that cooled the liquids in the debutanizer shut down based on the associated process conditions as per its original design. Hence, the heat inherent to the liquids in the debutanizer was no longer being effectively extracted, increasing the temperature and accelerating the vaporization rate. This ultimately caused the pressure in the debutanizer to increase significantly, and it peaked, in this case, at 12.6 bar gauge. At 8:52, the liquid level in the high-pressure separator went over range, which is to say it was greater than 100%, as a result of the main fractioner continuing to supply liquid to the process. At this point, the pressure had backed up in the system to a point where the overhead accumulator caused the pressure relief valve to open to about 28%. This vented vapor and gas via the flare knockout drum. At 8:53 a.m., the level in the knockout drum had risen by 10% to 70% in the space of only 2 minutes. At 9:12 a.m., the debutanizer outlet valve FV436 was indicated as starting to open as liquid levels in the recovery section began to re-establish, and by 9:40 a.m. the command to fully open the valve was sent to it. However, level indicators in adjacent vessels indicated no relative change, which suggests the outlet valve wasn't seeing any flow pass through it. In fact, it may not have even been open. With the intended outlet path now blocked, liquids began to accumulate in the debutanizer column and upstream, which led to the mixture of gases changing as the debutanizer was now effectively not extracting solely the lighter gas fractions from the material. The flaring generated a significant amount of smoke, though, and a plant operator was dispatched to check on the pressure sustaining valves that were venting, or PSVs for short. It was noticed that one valve had not reseated after the pressure spike, and the plant operator changed over operation to a spare relief valve from the top of the debutanizer. By 9 a.m, the plant upsets had led to an additional operator being brought to site for assistance. By 9:30 a.m, the temperature in the debutanizer had climbed enough that operators decided to bypass the heat exchanger in an attempt to reduce the temperature. But even with this, by 9:37 a.m, the pressure was rising too close to the PSV set pressure. To avoid further venting, the operators manually opened a bypass valve, HCV 439, to direct what was assumed to be uncondensed vapor from the debutanizer's overhead accumulator to the wet gas interstage drum. Unfortunately, because the level indication was incorrect, liquid as well as gas was sent to the wet gas compressor. Keeping in mind that liquids are incompressible, so that's not good, and now the compressor is taking on additional flow from two sources instead of one, and it includes liquid. By 9:40 a.m, the temperature in the debutanizer had reached 187 degrees Celsius, that's 369 degrees Fahrenheit, and continued to rise. The debutanizer level continued to read 79% of full range, despite the fact that ancillary readings suggested it had risen far beyond this. By 10:01 a.m, the debutanizer was filled with liquid, and the pressure in the vessel once again exceeded the PSV set pressure, this time peaking at 12.2 bar gauge. The PSV lifted for 16 continuous minutes and led to a corresponding rise from 61 to 93% in the knockout drum during that period. The additional liquid flow into the wet gas compressor had led to a carryover from the wet to the dry end of the compressor, leading to a compressor trip at 10:08 a.m. At 10:56 a.m, an instrument technician confirmed the reason for the trip was a high liquid level at the dry end, and HCV 439 that had previously been opened was closed. At 11:30 a.m, a discussion by operations personnel decided to attempt a restart of the wet gas compressor, despite the fact that there was no clear reason to them as to what had caused the trip in the first place. However, in order to restart the wet gas compressor, two steam hoses were attached to the outlet pipe at the dry end, and excess liquid was drained to the flare header. Not exactly a standard procedure. At 12:28 p.m, the wet gas compressor was successfully restarted. However, in the time it had been offline, the flow to the recovery section continued at a rate of approximately 230 cubic meters per hour because the flow had nowhere else to go. Within 18 minutes of restarting the compressor, the debutanizer pressure had begun to rise again, not surprisingly, once again exceeding the PSV set pressure, peaking at 12.8 bar gauge this time. More and more alarms came in, with each PSV lift peaking pressures and subsequent trips. Between 12:40 p.m. and the incident, the flow was estimated to have peaked at 110 kilograms per second, averaging at about 82 kilograms per second. In order to reduce the pressure in the debutanizer, the operators once again reopened HCV 439, this time to about 55%, which had the same result as previously. The interstage drum wet end level rose, this time from 7% to 60%. At 12:56 p.m, the high level in the knockout drum was reached, and the high level activates at 130 cubic meters of liquid in the flare drum, which also had a plant klaxon sounder attached to it. The matching alarm in the control room alarm page was never acknowledged, most likely due to the large volume of alarms now up and visible on operators' screens. At 1:03 p.m, the operators took the standby wet gas compressor pump offline, with the wet end reading only 8% level, and by all available information seemed to be operating correctly. At 1:10 p.m, the operators again further opened HCV 439 to 80%, and then minutes later to only 100% fully open, in an increasingly desperate attempt to reduce the pressure in the debutanizer. This additional flow went into the wet gas compressor interstage. By 1:12 p.m, the operators in the control room had accumulated well over 5 pages of alarm displays, With all the process upsets, trips and overrides, the alarm screens, which could handle 20 alarms per screen with a limit of 5 screens maximum, were unable to see alarms that had occurred only 60 seconds before. Operators in the control room focused on clearing and acknowledging alarms in an attempt to keep up with what was happening in the plant in real time. At 1:15 p.m., the field operator requested that the standby unit in the wet gas compressor be brought back online as the wet end level continued to climb. At 1:18 p.m., now only 5 minutes from the incident, the interstage drum wet end level reached 67%, and in an effort to prevent a second wet gas compressor trip, the field operator was instructed to open the bypass to the dry end drain valve. Even with this, however, unfortunately, it did not prevent the trip occurring at 1:21 p.m., just 3 minutes later. At 1:22 p.m., the main fractional column overhead pressure control valve, PV077, reached 63% open, as there was no more flow path via the wet gas compressor, and that sent even more flow to the knockout drum. At this point, the knockout drum had exceeded its design capacity, with high-velocity gas passing over the liquid surface, causing carryover of concentrated liquids, which were then exhausted through the flare. At 1:23 p.m., the outlet pipe from the flare drum was torn apart at the second elbow joint beyond the drum outlet due to the heavier and higher flow pressures, exhausting an estimated 10 to 20 tons of hydrocarbon liquid droplets and vapor into the atmosphere. Within 20 seconds of the vapor cloud release, it had mixed with air, reached its lower explosive limit, found an ignition source 110 meters from the venting point, and subsequently exploded. The force of the explosion was estimated to be the equivalent of 4 tons of high explosives. 26 people that were on the site at the time of the explosion were injured. The site overall sustained significant damage to equipment near the point of the explosion, and some properties in Milford Haven, 3 kilometres or 2 miles across the other side of the waterway, sustained damage to their windows. The shock wave rattled doors and windows as far as 16 kilometres or 10 miles away, and was heard audibly up to 64 kilometres or 40 miles away. The fire brigade locally wasn't staffed well enough to handle the incident, pulling in additional firefighters from as far as Cardiff and Swansea to assist, with 130 in total responding to the incident. The fire that continued at the flare drum was allowed to burn itself out until late in the evening on Tuesday, the 26th of July, since the local fire brigade were unable to operate the flare relief system since it had been heavily damaged by the explosion. Instead, they focused on preventing the fire from spreading to other plant areas and causing any further damage. Luck, not design, had prevented fatalities. The incident had occurred on a Sunday afternoon, which is one of the lowest staffed times of the week, night shifts notwithstanding. A van filled with contract personnel was imminently about to enter what became the blast zone, and by chance, it did not. The permit hut that was heavily damaged in the explosion had a group of people exit purely by chance only moments before the blast. Before we go any further, I'd like to talk about our sponsor for this episode, and that is Makers for Good, formerly Extrasensory Devices. They're an innovative company based in Palo Alto, California, and they've recently released the HELIO, a solar-powered lantern light, flashlight, and power bank. The HELIO has an intensely bright flashlight at 150 lumens, but if that's too bright, or you want longevity, it has medium and low light settings as well. The same too for its lantern light, but as a bonus, the lantern light also provides a red light as well as a white light. There's also an emergency flashing mode in case you need a signal for help. The HELIO takes 17 hours of full sunlight to fully charge from flat, and yes, it would take a couple of days to charge, but after that, you get 15 hours of lantern or flashlight. At 5,200 mAh, a fully charged HELIO can recharge an iPhone X in 1.5 times. Now, if that isn't impressive enough, I mentioned low light before. If you're using a medium light output, you'll get 5 continuous days worth of light, and in low light output, you get a whopping 1 month of light without ever needing to recharge. If solar isn't available, it can be charged from a standard USB port from flat in 6 hours using a standard micro USB connector if you need to. The HELIO comes in a variety of colours, redwoods, moonrock grey and adventure green, and all models come with a convenient flip-out stand hook that can be used to suspend the HELIO from a hook or stand it upright on a flat surface. It also comes with a convenient lanyard for carrying, and 3 low-power LEDs indicate its overall charge level. All the ports are protected by a tight water-resistant cover, and the stand is all metal, with a solid metal ratchet mechanism that holds it in place. The first thing that strikes you about the HELIO when you hold it is how strong and solid it feels. It's made from a high-strength polycarbonate case that's impact-resistant, and the unit weighs in at 370 grams, that's 13 ounces. All of that, and it's not much bigger than an average-sized mag light, measuring about 8 inches long by 2.5 wide and just over an inch thick. That's about 200 by 60 by 30 millimeters, so it's pretty portable. For a solid product like this, it's not built down to a price, but rather to its performance, which speaks for itself. The HELIO is only $89.95, but there's something different we really need to mention. Makers for Good have a non-profit arm, and as part of that, all of their profits from sales of the HELIO are used to support non-profit organizations through their Share Light program. Their ultimate goal is to help bring renewable and safer light and energy to parts of the world still reliant on kerosene and candles in a package that's just as at home anywhere in the world. So if you'd like to check one out, just head over to makers4, as in the number 4, good, or one word, .com/engineered to learn more and enter the coupon code ENGINEERED for 20% off your HELIO in your color of choice, and shipping is free anywhere in the continental United States. Thank you to Makers for Good for sponsoring the Engineered Network. So what went wrong? Firstly, a control valve was indicating to the operator that it was open. However, it was in fact closed. That misinformation led to several incorrect operator decisions. Operators attempted to keep the unit running when it quite possibly should have been shut down. Shutdowns, however, cost money. They take a long time, not just to shut down, but to restart. And ultimately, the push is always to keep production running and avoid shutdowns at all costs. The debutanizer outlet valve FV436 was tested after the event, and intermittent faults on the position indicator may have led to excessive wear on the valve plug. This ultimately leads to this valve most likely never opening during the event, meaning it was effectively stuck, completely closed. The debutanizer level, and in fact many other level transmitters in the plant, had been designed to be accurate over their normal operational range, not their minimum and maximum possible ranges. It was a common practice at the time, and the same issue experienced at BP Texas City on the ISOM unit, which was a contributing factor in that incident as well in the coming decade. There was also corrosion in the flare line. The weak spot in the flare line that ultimately failed under stress was measured at being only 0.3 millimeters thick and completely unable to withstand the design value of 3.4 bar gauge, let alone that which it experienced during the incident. Although the company had recognized that corrosion on the flare line was an issue, the inspections that they were holding did not cover the specific area that failed. In fact, they just covered the more visually exposed areas instead. In addition, their risk mitigation measure was to temporarily use pipe saver clamps that could be applied prior to a shutdown, thinking more about the normal use of the flare line in the lead up to a planned shutdown rather than the worst case incident where fitting such protection wouldn't be possible due to a lack of time available. Had the flare line been sufficiently sized to handle the additional pressure, the higher pressure and flow could have been directed away from the unintended ignition sources and flared safely without incident. That said, it should never have reached that stage in the first place. There were 14 recommendations made by the investigators. We're going to focus on 3. Safety critical testing, number 7. Process displays, number 3. And alarm management, number 6. That's not to say that the other recommendations weren't important, because they were. However, these 3 in particular specifically apply to my day-to-day job. Safety critical testing first. Recommendation 7 reads, and I quote, "Safety critical plant elements on which the safety of a process relies, i.e., whose failure could lead to a hazardous event, should be identified. Any safety system used to protect against hazardous events should be specified and subsequently designed based on an appropriate hazard and risk analysis so that the functions be carried out and the necessary level of integrity are systematically determined." End quote. There were 6 devices used for safety protection in the plant that were found to be inoperable during the incident investigation. Whilst the safety controller existed, there was no rigorous testing of safety critical elements. no requirement to ensure operability on a regular basis, and no identification in the control system of what alarms related specifically to safety-critical elements. If there's a safety-critical element, or what's referred to as the final element, then regulations today require that it's regularly tested with records proving that this is the case. Process risks should be analysed during design via a specific design review referred to as a HAZOP, which stands for a HAZOP operability study. And if evaluated as being above a set threshold, then it undergoes a secondary review called a LOPA, a layers of protection analysis. The LOPA then sets the minimum required protection level, or safety instrumented level, SIL for short, which dictates equipment that can be used, the test regularity as well of the final element. At the time of the incident, however, this was not mandated, nor was it standard practice. The second recommendation relates to mass balance. And I quote, "Display systems should be configured to provide an overview of the condition of the process, including, where appropriate, mass and volumetric balance summaries." End quote. And what they mean by that is flow in versus flow out, or overall plant balance. Rather unfortunately, this was also a factor in the BP Texas City refinery explosion a decade later. Only recently, with ASM guidelines evolving and extending into the ISO 101 standard, it's the first true standard of its kind that can be regulated, do we actually have a chance as an industry to move these collective learnings into control system visualization design. From non-fatal personal experiences, I know that these concepts make sense and are correct. However, education for younger control system user interface designers needs to include lessons like this one. Badly designed user interfaces were a contributing factor to this incident undeniably. Operators had lost their overall perspective of the process and made decisions based on the localized flows in a single component of the process at a time, not thinking through all the consequences of flow changes throughout the entire process before and after. It's clearly understood that in pressure situations, human beings struggle with logical thinking. If the layout of your HMI is such that the operator needs to add and subtract a bunch of numbers after they've thought through their mental mind map of what the process looks like, you're asking for trouble. HMI should be designed for when operators are under extreme duress, not just for normal plant operation. And that's because people make mistakes under pressure. So figure out when you're designing the plant, what does the operator need to know, need to see, and need to understand in a crisis situation. And that's what guides what goes on screens and how they're laid out. The last recommendation I want to look at relates to alarm management. And I quote, "The use and configuration of alarms should be such that A, safety-critical alarms, including those for flare systems, are distinguishable from other operational alarms. B, alarms are limited to the number that an operator can effectively monitor. And C, ultimately, plant safety should not rely on operator response to a control system alarm." End quote. I added the A, B, and C because I wanted to highlight just the one, B. How many alarms can an operator effectively monitor? The investigation uncovered that in the 11 minutes leading up to the incident, the operators had to acknowledge and in some cases attempt to act on 275 alarms, which between two operators equates to an average of 25 alarms per minute, or one alarm every 5 seconds. In total, there were 2,040 alarms configured in the entire system, many of which were classified as visual and audible priority ones. However, a subsequent rationalization effort showed that the vast majority weren't actionable by operators, but were in fact just for information. In fact, 87% of the alarms were listed as high or above, with a misclassification of alarm priorities rampant throughout the entire system. There was also a lack of training about how the operator should respond to specific alarms. And importantly, there was no distinction between safety-related or safety-critical alarms relative to normal process or equipment alarms. When you're developing an alarm system, having a cause, consequence, and action that the operator can actually take for every alarm is essential. Bigger plants have more alarms, meaning you need to be able to look them up quickly. Some HMIs now integrate this functionality into them such that when an alarm goes off, an information window can be brought up in seconds to indicate the advisable course of action that the operator should consider. Importantly, though, the operator must be able to do something, or it isn't worth telling them. If there's a low battery on a UPS system, but you're on main supply and you have a backup UPS in parallel anyway, then is that low battery really a high priority alarm? That's just one example. I mean, of course that's not. If you've got a high level in the knockout drum going to a flare line, yes, you should please tell the operator that. And of course they did, but it got drowned out by all of the nonsense. One of the reasons that this went badly is because the operators spent most of their time during the last minutes before the explosion looking through nuisance alarms. These process alarms that had gone off repeatedly between trips and high levels and high levels and low levels. It did not help at all. Rather like a denial of service attack on the internet, alarm information overload had a similar effect on the human beings in this case. Rebuilding the plant cost approximately £48 million. Texaco Limited and Gulf Oil Limited were fined by the Swansea Crown Court on the 22nd of November 1996 to the value of £200,000, plus £150,000 in legal costs. Milford Haven amazes me personally because it was a key moment in the evolution of safety instrumented systems as well as alarm management and user interface design for control systems. The Engineering Equipment and Materials Users Association, or EEMUA for short, developed the EEMUA 191 standard and released it in 1999 primarily as a result of Milford Haven. In coming years, the International Society for Automation, or ISA, extended and refined to what has now become the ISA 18.2 standard and is the current basis for all alarm management designed and implemented today. It lent weight to what has become accepted standard minimum requirements in all of those areas of engineering I mentioned previously. Nobody died, and that's great, but that was just dumb luck rather than good planning and good design, because it was neither of those. The lessons that we learn from Milford Haven may seem subtle, perhaps, at first glance, but they are far from that. They are very instructive and very decisive if you think them through. And whilst many people in this industry have heard of it, very few outside of the industry know anything about it. I hope now that others have a better understanding of exactly what went wrong at Milford Haven, and to make sure that they minimize the risks of it ever happening again. If you're enjoying Causality and want to support the show, you can, like some of our backers, Chris Stone and Carsten Hansen. They and many others are patrons of the show via Patreon, and you can find it at patreon.com/John Chidgey, or one word. Patron rewards include a named thank you on the website, a named thank you at the end of episodes, access to pages of raw show notes, as well as ad-free, higher quality releases of every episode. So if you'd like to contribute something, anything at all, there's lots of great rewards, and beyond that, it's all very much appreciated. I'd like to thank Makers for Good for sponsoring the Engineered Network. Visit makers4, as in the number 4, good, or one word, .com/engineered for more information about their impressive HELIO solar-powered light, flashlight, and Powerbank, and use the coupon code ENGINEERED for 20% off exclusively for Engineered Network listeners. Causality is part of the Engineered Network, and you can find it at engineered.network, and you can follow me on Mastodon at chidgey@engineered.space, or the network on Twitter at engineered_net. This was Causality. I'm John Chidgey. Thanks so much for listening.